So when titrating strong base into a weak acid, we see a pH curve like this one. Like we did last time, or like we've done previously, we need to have a look at the or determine the equivalence point. So again, extrapolate forward, extrapolate back, vertical portion, okay, and read down to this point here. So this is going to be our volume at the equivalence point. Okay, we can also call that the equivalence volume. We can read along, so if we take half of that distance there, so that's 80, so roughly there, read along, we will see that the pH is greater than 7. Now, a strange thing happens when we set up this particular pH curve, and that is, if we look at the equilibrium of the Ka, it's going to be equal to H plus A minus divided by the HA, because in here we've got a weak acid which is going to be making, during the reaction, is going to be making H plus and A minus. When we add OH, we actually react it with the HA and the H plus, but we also produce A minus. And if we look at the equivalence point, so the volume at the equivalence point, what we're saying is that the concentration, or the number of moles of the HA, is equal to the number of moles of OH minus. But if we look at the half equivalence point, so if we take, for example, if this was 25 centimeters cubed, if we were to look at half the equivalence point, so this is half equivalent, and that would be 12.5 centimeters cubed, and we were to read up from there and then across from there, whatever this pH value here, it would be equal to the pKa. And the reason for that is because at the half equivalence point, the number of A minuses, so at this point here, the number of moles of A minus is going to be exactly the same as the number of moles of weak acid that's left, which means that they will cancel out. So Ka will be equal to the concentration of H plus, which also means if we take logs of them, the pKa will be equal to the pH.